This is one of these places that I heard about from my oceanography colleagues at Duke for years. Bruce Corliss in particular. This is kind of he got his PhD here, so I guess it was sort of his alma mater and the motherhood of oceanography. And so it's a great honor to be here today. I will unabashedly say that the subject of my talk today will probably pretty much stop at the coast. I'm going to dump nitrogen into the ocean and let you people deal with it then. But it will give kind of a terrestrial view of where nitrogen is coming from, the origin of what I think will increasingly be recognized as the nitrogen problem. I think this is the next big element for policy makers to consider. Therefore, it will be the next big element for the journalistic and media world to educate the general public on. And I've had a great time trying to help with that process over the years with greater or lesser success. Mostly when I read blogs, I think the success is lesser, but we have a lot of work to do, and I think this one will be an upcoming issue that we'll all want to know about it. So this is my title today, Chasing Nitrogen Atoms, a Global Nitrogen Cycle. And I want to stress from the beginning that this is, in a very real sense, ecosystem science at its largest scale. We're going to deal with kind of the planetary ecosystem here. Of course, we have no replicates of that are meaningful in an experimental way, so one has to do ecosystem science at the global level by correlation, by modeling, by looking at the past, the geologic record, paleo record of, in this case, how nitrogen was moving on the planet, and infer the accuracy of models by seeing if they predict the past with any degree of accuracy. And so this is my title, Chasing Nitrogen Atoms, the Global Nitrogen Cycle. Scott had a wonderful introduction, almost embarrassing. But I've had a great time to plug global biogeochemistry a little bit. I've had a great time over my career. It started actually when I was an undergraduate with exposure to a couple of professors at Dartmouth that really found some interesting ways, or at least interesting to me as an undergraduate, of thinking about the Earth as an interconnected ecosystem. That, of course, Gene Likens and Herb Borman were there getting the Hubbard Brook experiment started, and thinking about watersheds and the chemical elements that flow through watersheds. But this really is a larger view, taking a view of the Earth as a chemical system, movements of things between the atmosphere and the oceans and the land surface, that all were interconnected, and essentially good evidence that life on Earth, almost in a Gaia-esque fashion, but I don't want to say I'm a Gaia creature of following here, but life certainly determines a number of properties on the surface of the planet, and of course a number of those properties have been conducive to life for 3.5 billion years. So it's important to understand what the Earth has gone through when it's had perturbations, bolides coming in and sterilizing its surface, and volcanic eruptions and big glaciations. What did all that do to the chemical composition of the surface of the Earth? What did it do to the creatures that lived on the surface? How did they bounce back? And how do they determine some of those chemical conditions themselves? So that's really been the name of my game, and I want to convince you that this is an exciting approach that is a lot of fun and absolutely relevant to policy makers and the media today. And of course, we can look at that from the surface of the moon when the astronauts first went there, nearly 40 years ago now, and look back at the Earth. There you get the feeling that that's a very special place against the blackness of space that has harbored life for some 3.5 billion years, maybe 3.8, and we need to treat it well and to understand those processes. Now, I have had a lot of luck over the years trying to take pictures of the Earth and bring them down to these, what I call cartoons of the geochemical cycles. I put boron on here today because Art Spivak, I know, is here, and he may even be in the room. There he is, who knows a whole lot about boron, and actually a lot of his work went in to this particular diagram. But it doesn't really matter that it's boron or not. We're going to spend the rest of the day on nitrogen. But for these few moments, we'll look at boron. But if you identify the major processes that move boron around on the surface of the Earth, that gives you a stark realization that some of those are human activities, in this case mining and industrial activities. And if you can quantify the input, in this case of boron to the atmosphere, largely as boric acid vapor to the atmosphere or volatilized boron, it gives you some perspective of the human impact compared to these various natural movements. And of course, that's the first thing that a policymaker asks you in Washington for the carbon cycle and climate change and the nitrogen cycle and fertilizer pollution is, well, gee, it's been happening for years. Volcanoes do this. What difference do humans make? And these kinds of diagrams can really set that forward in a clear sense for those kinds of situations. And I think increasingly, when simplified enough, they're kind of useful for the journalistic world as well and the readership that they have to address. So from a science point of view, you can take that kind of diagram. And I've done this for some of the important chemical elements at the upper end of the periodic table, important to living things, specifically carbon and nitrogen are the ones we hear the most about, in which in units of 10 to the 12 grams or teragrams of stuff moving around on the surface of the Earth. It's a large enough unit, it's really hard to let alone get your hands around, but even get a mental concept of it. But that turns to be the unit of choice in many cases. You can quantify what the biological cycle is, let's say for the year 1600 AD, before humans really had a very large population and before the Industrial Revolution. So this carbon biotic cycle, that's largely photosynthesis and respiration by living things on the land and in the ocean. Nitrogen uptake, nitrogen fixation. Phosphorus, that's really the mobilization of phosphorus in rock weathering and chemical weathering of the surface, and so on. And then the second column here are really, well, this is the effect of Homo sapiens, you and me, a single species that's really dominated the planet for the last 150 to 200 years with our ability to mine the crust and move elements from the crust of the Earth into this biotic cycle much more rapidly than they were pre-industrially. So this 7,000 teragrams in carbon, notice it's about 6% of the, nearly 7% of the natural cycle, but that's all the mining of fossil fuels, coal, oil, natural gas out of the crust of the Earth, burning them, mobilizing them into the atmosphere where they can cycle rapidly with the biosphere. The fact that there's an IPCC, a Kyoto Protocol debate over the Waxman-Markey bill in Congress right now, that all stems from recognizing this roughly 7% perturbation by you and me, Homo sapiens, of the carbon cycle with the potential resulting impacts on climate. As I said, today I want to focus on nitrogen. The impact is right now recognized as slightly less, something on the order of 2% globally. We'll see it's a little larger than that when we just confine our purview to the land surface. But we're beginning to see problems crop up with hypoxia in the Gulf of Mexico, eutrophication of a number of natural waterways, pollution of groundwater, various air pollution aspects that are very much related to the incidence of emphysema and asthma, increasing incidence in human populations throughout the globe. So that's really our focus today. But you can see you can do this for all these elements, and the basis of that is sitting down, either formally or just on your napkin at lunch, putting together one of those pictorial cartoon diagrams of the cycle and seeing how humans fit into to things. And of course, they're always they're never done. You can update them endlessly. So there's always something for your next graduate student to do.